Okay, chapter 21.6, conjugate addition, also known as 1,4 addition and Michael addition. So I'll draw up. This is only going to happen when you have a carbonyl compound bonded directly to an alkene. Okay, so alpha beta. This is, we would call this an alpha beta, sorry, there's a comma there, unsaturated carbonyl. Right, so the alpha and beta carbons are unsaturated. They have an alkene, could be an alkyne, and in fact you can have other atoms in there, but it's almost always an alkene. All right, and the reaction is a nucleophile is going to add here. Okay, and why is that allowed? Well, you get an enolate out of it. Let's draw the whole thing. So the product ends up looking like this. And then this, throw some protons in, you're going to end up with addition out there. Okay, so that's called conjugate addition, and it differs from addition directly to the carbonyl compound. So you might imagine the nucleophile attacking here. This is what we've seen so far. And this is 1,2 addition. Okay, so if you look at this, the numbering is starting with the carbonyl oxygen being number 1. 1, 2, 3, 4. So adding here, O minus there, you technically protonating there, that's 1,4. If the nucleophile adds to the carbonyl compound, that's 1,2. All right, so we might refer to this is either 1,4 product or the Michael product. You're going to see a lot of different words used here. And this over here would be the 1,2 product. This is the normal addition to a carbonyl product. All right, so take that in. And so why does that happen? Well, if we think about resonance structures, right? So the 1,2, it's pretty easy to see why you'd get nucleophilic addition to the 1,2, right? So any carbonyl, all carbonyls are going to have this resonance structure where the pi electrons pop up onto the oxygen and you end up with a positive carbon. So there's significant partial positive charge on the carbonyl carbon. But you can also, now that these pi bonds are conjugated, you have a resonance structure that's got positive charge out on the beta carbon. And so this beta carbon is, so there's a very big partial positive there. There's a little bit smaller partial positive there, right? The resonance structure on the left is more stable than the resonance structure on the right, because on the left the charges are closer together. Okay, so again, conjugate addition, sometimes called 1,4 addition, sometimes called a Michael addition, is when a nucleophile adds to the beta carbon of an alpha beta unsaturated carbonyl. And it can do that, and then this will alternate. Okay, so you could imagine 1,6 addition, right? Draw resonance structures here. So now you could get 1,6 addition. Really, what it, you know, if there's chemistry of X, and you put this is a vinylogous X, that means nothing probably, right? So this double bond essentially being conjugated to whatever X is, that oftentimes the chemistry of the double bond will be reflected in the chemistry of X. Okay, so up until now, you guys have seen alkenes be nucleophiles. If you think back to Orgo 1, electrophilic addition to alkenes, the pi electrons in the alkene were nucleophilic. But when you bond the alkene to a carbonyl, like this, you're used to seeing carbonyls be electrophiles. Well, bonding it makes this alkene electrophilic. All right, let's look at some examples. All right, I'll just put a line in here. So how might this look? So draw the product of that. Hit pause and draw the product. If I treat cyclohexenone with sodium methylphthalate. All right, pause, come back. All right, good. So the product here is going to look like this. Right, sodium is going to be a plus, sulfur is a minus. And I guess I should have said, let's do this reaction in ethanol. If you drew an enolate product, that's fine. So let's say this reaction is in ethanol. Pop the electrons up here. You're going to get an enolate. And then the enolate will take a proton from the ethanol. Okay? So it's a 1,4 addition. That's a 1,4 product. That's the 1,4 product. Let's do another one. Okay, so draw the product, what you get if you treat cyclohexenone with methyl grignard and then proton. So hit pause, come up with the product. Okay, so you're back. Now, I fooled you. So this should make you feel like you're in class, right? Always putting up the wrong things. Here we see the 1,2 product. And the question you should have at this point is, why the difference? Okay, so we're going to go back. We're going to go back now. I'm going to slide this down. I'm not going to erase it. I'm going to slide this down. And this goes again to kinetic and thermodynamic products. So up here, shoot, I can put some of this here, right? So on these resonance structures, there's a very large partial positive charge on the carbonyl carbon. There's not quite as strong a partial positive charge on the beta carbon. That's because the left resonance structure, as the charges closer together, is more stable than the right structure, which has them farther apart. So the first thing, it is always true that 1,2 addition is fastest. Okay? So that's going to give us a 1,2 product. That always forms. And again, just like we did with kinetic versus thermodynamic enolates, the question then is, does that back reaction happen? So the more specific question is, can the O minus kick out nucleophile? Right? Okay, so now if you look at these down here, think about what you get from the 1,2 product here. Right, so thiomethoxide adds in 1,2. You have O minus bonded to a carbon with that thioether. That's an easy, right? O minus is a less stable base than S minus, so it just kicks it right back out. So the back reaction in this case is very fast. So if that happens, if we go back here, then eventually the nucleophile will add 1,4, and that's also reversible. So if the 1,2 is reversible, (1,4) must be as well. But in this case, you're going to reach equilibrium, and the equilibrium is going to favor the 1,4 product. So now if we protonate this, we'll get the 1,4 product. Okay. How does this play out with the Grignard reactions? Down here on the bottom, I guess I need to erase that. Down here on the bottom, this Grignard reaction. Grignard's going to add in 1, 2. Now, is that a reversible reaction? Would you expect that O- to kick out methyl minus or any of the R minuses? And the answer is no. There's no back reaction here. That means you get the 1,2 product. Okay, so for any nucleophile that you look at with the Michael reaction, you should look at what happens when the nucleophile adds in 1,2 to the carbonyl. If the back reaction happens, that nucleophile is most likely going to add 1,4. If the back reaction can happen, then the nucleophile is most likely going to add 1,2. And we can actually specify this, so this comes back here. We can look at this again. The question is, right, does the reverse reaction happen? If it doesn't, you get a 1,2 product. If it does, you get 1,4. All right, so I can give you a list. I'd like you to understand this, but if not, you can just memorize it. So 1,2 is favored with Grignards. Lithiums. Enolates. Yeah, that's it. Okay, so when you have an unstabilized enolate, right? So if you just have if you're just doing an aldol reaction, 1,2 is going to be favored. About 1,4 addition. So alkoxides, sulfides, so this would also be RSH, and dicarbonyl enolates. Also, also enamines. That's going to be 21.7, I think. No, that's still 21.6, sorry. Stuart, I'll do a video on that. Okay, so again, if the nucleophile can be kicked back out from here, so if you just draw this product, and just imagine, it doesn't matter how you get to it, but if you've got a nucleophile, if you've got something attached to a carbon that's bonded to an O-, can the O- kick that out to give a carbonyl and release the nucleophile? So that sort of comes down, is the nucleophile a weaker base than O-? If it is, it gets kicked out. Okay, so again, the nucleophiles where 1,2 addition is favored are Grignards, organolithiums, anything where you have a super strong nucleophile, single carbonyl enolates. So anything that would do an aldol reaction typically is going to add 1,2. The nucleophiles that are favored for 1,4 addition are going to be alkoxides, sulfides, thiols, dicarbonyl enolates, sort of a stabilized enolate, and enamines. So 20. That's going to be something called the Stork reaction. Okay, so I'll put up some examples in a bit and do one more video on Stork.